Welcome! I am absolutely thrilled you're joining me today for another deep dive on this explainer. Today we're looking at a piece of technology that honestly sounds like it belongs on a starship, but it's actually revolutionizing modern biomedical diagnostics right here on Earth. We are talking about surface plasmon resonance, or SPR. If you've ever wondered how scientists manage to monitor the invisible, microscopic world of biological processes in real time, well, you're in exactly the right place.
To really grasp why this technology is such a game changer, we have to start with a fundamental problem. How do we detect completely invisible molecules in real time without altering them in the process? Think about it like trying to observe two people shaking hands in a pitch-black room. If you turn on a massive, blinding spotlight so you can see them, or, say, paint their hands with glowing dye, you're probably going to change how they interact, right? For decades, scientists faced this exact same dilemma when trying to measure biological targets on a microscopic level.
Okay, let's dive into this. Here is our structure and roadmap for today. We're going to cover 1. Seeing the invisible. 2. What is SPR? 3. The physics of plasmons. 4. Reading the sensogram. 5. Real-world applications. And 6. The future of biosensors. Section 1. Seeing the invisible and the detection dilemma.
So, traditional optical biosensors relied heavily on this really complex fluorescent labeling. You basically had to attach a glowing tag to your target and wash away all the unbound molecules. It was a slow, clunky process that could literally change the fundamental nature of the molecule you were trying to study. SPR, on the other hand, is a total paradigm shift. It allows for label-free detection, in real time. You get this dynamic, continuous stream of data on unmodified molecules exactly as they exist naturally, with absolutely no washing steps required.
Section 2. What is SPR? Defining the core phenomenon. Okay, so what exactly is surface plasmon resonance? Basically, it's an optical phenomenon that happens at the boundary between a metal and a non-conductive medium, usually between a super thin metal sheet and a liquid. When polarized light hits that boundary at a very specific angle, it actually excites the surface electrons of the metal, which reduces the intensity of the light bouncing back. Now, the absolutely crucial takeaway here, that reduction in light is directly proportional to the mass of the molecules accumulating on the surface. We are essentially weighing microscopic molecules using nothing but light.
Section 3. The physics of plasmons, a microscopic journey. Everything starts with a single light source. Picture a beam of polarized light directed upward through a really dense medium, like a piece of glass. It hits the boundary between the glass and the air above it, and it undergoes what physicists call total internal reflection. It's kind of like skipping a stone across a really calm pond. The light bounces perfectly off the inside of that glass surface.
Now here's where things get really interesting. We sneak in a tiny, incredibly thin metal film, usually gold, right at that boundary layer between the glass and the surrounding environment. Notice that we haven't changed the light itself at all, but we have completely changed the conditions at that boundary. Because we added that gold, the physics totally shift. When that polarized light hits the gold sheet at a very specific, critical angle, which we call the resonance angle, not all of the light bounces back. A portion of that light energy transfers directly into the gold itself, and this creates a literal dark zone, or a dip in the reflected light that hits the detector. It basically casts a highly sensitive optical shadow. So, where did that missing light energy actually go? It certainly hasn't vanished, right? Well, that energy from the light was absorbed by the free electrons living in that thin gold sheet. The absorbed energy excites those electrons, making them wildly oscillate and travel parallel to the sheet. And that group of excited, oscillating electrons, that is what we call a surface plasmon. The exact angle where this whole resonance thing happens is incredibly sensitive to whatever material is sitting right on top of that gold layer. In a biosensor, we attach specific receptors to the gold. When a target molecule, the ligand or analyte, flows over and binds to those receptors, the mass increases. This shifts the refractive index, which literally changes the exact angle required to trigger the plasmon. So, as molecules bind, that dark zone shadow actually moves along the detector. It's operating exactly like an inconceivably delicate optical scale.
Section 4. Reading the sensogram. Let's translate this physics into data.
We call this whole setup the Plasmon configuration. And the brilliance of this system is that it constantly monitors the exact position of that moving optical shadow and plots it on a graph over time. This continuous, real-time plotting generates something called a sensogram. It allows scientists to track biomolecular interactions as they happen, without ever taking their eyes off the reaction. The sensogram is essentially telling us a second-by-second story of these molecules, and it happens in 4 distinct phases. First, the baseline, where just a clear buffer flows over bare receptors. Second, association. This is where the target analyte is introduced. It binds to the receptors, the mass goes up, and the signal rises. Third is equilibrium. The surface is completely saturated, meaning molecules are binding and unbinding at the exact same rate, which flattens the curve. And finally, dissociation. We switch back to a clear buffer wash, the bound molecules let go, and the signal drops right back down as the mass decreases.
Because this entire story unfolds in real time, scientists aren't just seeing if the molecules bind, but exactly how they bind. From this specific curve, researchers extract what are called kinetic constants. They calculate K-on, the association rate, which tells us how fast molecules recognize each other and grab on, and they calculate K-off, the dissociation rate, which tells us just how stable that bond is before they let go. Traditional endpoint tests literally cannot give you this level of dynamic detail.
Section 5, Real-World Applications. Moving from the lab to real life.
So why does all this dense optical physics actually matter to us? Well, SPR technology directly protects human health through some truly crucial real-world applications. Take medical diagnosis, for example. SPR is used for the immediate detection of acute myocardial infarction, a heart attack, by instantly reading levels of cardiac troponin in the blood. During a heart attack, every single second matters. Real-time, label-free detection enables immediate, life-saving point-of-care decisions. It's also huge in environmental monitoring. SPR sensors can track heavy metal ions and agricultural herbicides in water supplies. Because it barely needs any sample volume, we get fast, highly accurate field detection of pollution long before it hits our communities.
And to put into perspective just how mind-bogglingly sensitive this light-shadow scale truly is, get this. The SPR method can detect an accumulation on the sensor surface of just 1 picogram per square millimeter. That is 1/trillionth of a gram. This minuscule mass change corresponds to a shift of approximately 1 microrefractive index unit, which in SPR data is just called 1 RU. The precision here is just incredible.
Section 6. The future of biosensors. What's next?
Looking ahead, the ultimate engineering goal is moving SPR out of bulky, expensive laboratories and getting it out into the real world. That means a huge focus on portability, shrinking these complex optics down into small point-of-care clinical devices. It means integration, seamlessly combining SPR with the rapid diagnostic workflows doctors already use. It also involves multiplexing, so moving beyond just single targets by designing specialized arrays that can track multiple disease biomarkers at the exact same time. And of course, affordability. We have to balance the complexity of manufacturing these sensors with the reality of needing low-cost, widespread clinical use.
I want to leave you with a thought to ponder today. As SPR evolves from this dense laboratory optical experiment into portable, everyday point-of-care devices, how might real-time, molecular-level diagnostics change the future of your own healthcare? Imagine a world where your doctor isn't waiting days for a lab result, but is instead watching your biology interact in real time right there in the exam room, all thanks to the physics of light and shadows. Thank you so much for joining me on this explainer. I really hope you found it as fascinating as I do. Keep asking questions, and I will see you next time.